In this video, we're going to look at calculations with a heat transfer. This is actually very similar to what we're going to end up doing in the lab. There's going to be a transfer of heat from something hot to something cool. There's always going to be an endothermic component and an exothermic component in a heat transfer. So we have a 5-gram piece of aluminum that was heated from 25 degrees to 78 degrees. Then added to 100 milliliters of water at 20 degrees. How much energy is transferred from the hot metal to the cool water? Okay, so here's part of it. The energy is transferred from something hot to something cool. So for the metal, it's going to be an exothermic change. The hot metal, this is going to be exothermic. The metal is going to release its energy to the cool water. The water is going to absorb the energy. This will be endothermic for the water. So visually, think of it like this. Here's a beaker. It's full with water. We'll say cool water. Cool water. And then we add a hot piece of metal. It's a metal at 78 degrees. So we're going to use these little metal cylinders. Let's call this hot metal. Hot metal. We can sneak it in there. Hot metal. So the heat will flow from the metal to the water. So kind of in this manner. There we go. Energy will be released from the metal, absorbed by the surrounding water. Predict the final temperature of the water after the hot metal is added. So if this is an endothermic change for the water, if I'm adding a hot piece of metal, I'm expecting the water temperature to increase, right? The final temperature should be something greater than 20 degrees. So here's the heat transfer part. Let's figure out how much energy can be transferred from the hot metal. And then it should be absorbed by the cool water. So this is going to be for the metal. Let's figure out how much energy is in this piece of metal. Delta H equals mass of the metal. This is a 5-gram piece of aluminum that was heated. 5 grams from 25 degrees to 78. So temperature change is final minus initial. Excellent. Or if you would prefer, you could just plug this in as a 53-degree temperature change. And then since I know that it's aluminum, I can flip back a couple pages and look up the specific heat. Aluminum is 0.897 joules per gram degree Celsius. So let's plug it all in. Maybe 237.7 joules. So here's all the energy from that hot piece of metal when it was heated from 25 degrees to 78 degrees. Now, assuming no sources of error, all the energy from the hot metal should be transferred to the cool water. So we just answered the first question here. How much energy is transferred from the hot metal to the cool water? Should be this guy. 237.7 joules. The energy from the warm metal should be transferred to the cool water. Assuming no errors, such as heat loss to the surroundings. So when we really do this in the lab, we're going to have some errors. And there will be heat loss to the surrounding air, maybe to the beaker. But assuming no errors, there should be a total transfer of heat. Now we can use this delta H value to predict the final temperature of the water after the hot metal has been added. Okay, so we're going to set up this equation again, but this time in reference to the water. So the water is going to absorb all of this energy. So this is my delta H value. to 37.7 joules. So that's again why they call it a transfer of heat. Often there's one particle that you know everything you need in order to calculate the delta H, the heat, and then you'll transfer that heat to the second particle. And then often we'll solve for one of the other missing variables, like mass, temperature, specific heat. In this particular question, we're going to solve for the temperature change. So what do we got here? It was 100 milliliters of water, which is 100 grams. We'll leave temperature change as our variable. The water is starting at 20 degrees, and I'm going to assume that this isn't enough energy to vaporize the water. So we'll use the specific heat of water in the liquid phase, the 4.18 joules per gram degree Celsius. Awesome. Now we just plug this in and solve for the temperature. Delta T is, do my algebra, ooh, interesting. It's really small. Maybe like 0.57 degrees Celsius. My temperature change is like a half degree. Which now again, you can use your noggin, or you can do a little bit of algebra. Temperature change is temperature final minus temperature initial, which they tell us it's 20 degrees. The temperature change then I could sub in, and maybe I'll just do that right away, as 0.57. 0.57 degrees. Which I'm going to get then just a temperature change of, a final temperature of 20.57 degrees Celsius. So there's kind of part 2. Here's kind of part 1. Now you may also just use your noggin. If I'm adding a hot piece of metal to the water temperature should increase. So that temperature change is a positive. The temperature should go up by 0.57 degrees. But now here's what I always just think is really interesting. So we had the same delta H. We have the same amount of heat from the metal to the water. When the metal absorbed this 237 joules of heat, the metal increased in temperature by a whopping 53 degrees. You add that same amount of energy to the water, temperature changed by like a half degree. They might ask you why. With the same amount of heat, why don't they have the same temperature change? And you might say, okay, well the mass is different, and yes it is. This is 100 grams. And so yeah, that heat is being distributed amongst a lot more particles. This one's only 5 grams. So yes, that would be a very good answer. And the other one, look at these guys, the specific heat value. The specific heat of water is like 4 times greater than the aluminum. More than 4 times greater. Which just means that it takes more than 4 times as much heat energy to increase the temperature of the water molecules. It all goes back to those strong hydrogen bonds. There are very strong intermolecular attractions between the water molecules. So it takes a lot of energy to start making them wiggle around more. So this is very typical. And I mean, yeah, obviously, yes, the mass is very different. But even if we had the same mass, the temperature change would be drastically different because of that darn specific heat value, those strong hydrogen bonds in water. Great question here. This is a typical transfer of heat type of calculation. Where again, you'll calculate the delta H for one particle, and then we assume that all the heat is transferred to the second substance. We can use the same numerical value, and then we just plug in our other variables for that second substance.